Okay, in this video we're going to estimate our first Bayesian model. So this will sort of be the equivalent of what you would do with an OLS regression. And to fully understand what we're doing when we're estimating the Bayesian model, we actually will estimate the model on simulated data. Yeah, so we simulate our own data so we know exactly what is happening, and we then also understand what the Bayesian model should pick up from this data. So by now you should be able to understand this function generating data. So this weird f here is my editor's way of showing the Python keyword def, the way you define a function. And this little symbol here is the way it sort of represents return. Yeah, so the thing that's returned by this function. And what's returned by this function is the data frame df. So this function generating data has a number of default values for its parameters, which are going to be slope parameters. So there is a variable a1, which I'm going to set equal to 1, a variable a2, which I'm going to set to -1, a variable b, which I set equal to 3, and a variable n, which I set equal to 100. So when I call the function without any arguments, like I'm doing here, Python will simply use the default values. So x1 is going to be my first variable. It's going to be normally distributed between 0 and 1. Yeah, so it's a normalized variable, mean 0, standard deviation 1. And I'm going to draw size n, so in this case 100 samples from this distribution to generate my variable x1. I do the same for variable x2. So again, I draw 100 samples from this normal distribution. I have a noise term, which again draws from normal distribution. And then my variable y is going to be equal to b, so b is the constant here, plus the slope of variable x1, so that's a1 times x1, a2 times x2, plus the noise term. Then out of these variables that I just generated, so y, x1 and x2, I generate the data frame, and the function generating data returns this data frame. Yeah, so when we run this, I now have a data frame with this data in it. Yeah, since this is random, you will have slightly different data than I have, so you will also get slightly different results in the Bayesian model. Yeah, so now we can start to generate the Bayesian model. So the syntax for that in pymc3, so we've imported pymc3 with the letters pm. So with pm model s, and now I give the name of the model, so the way I want to refer to this in my program below. So I call this model simulated data to distinguish it from models later on, where we're going to actually use Eurostat data. So with pm model s and then the name of my model, model simulated data, and now I can define what my model is. Yeah, so I start actually from the bottom up. So ops basically is the observed variable in my data. So I'm going to assume this is normally distributed. So I'm assuming that the variable y, which we just generated in the data generation above, I'm going to assume it's normally distributed. That's actually correct. Yeah, because noise, which is the thing that will generate the distribution of y, is indeed normally distributed. I repeat the name of the variable, which in this case is ops. Then I specify what mu is going to be for this variable. Yeah, so this is going to be normally distributed with a mu and a sigma. And the mu is going to be slope 1 times, from my data frame df, the variable x1, plus slope 2 times df, from my data frame the variable x2, plus a constant. Yeah, just note that, oops, should be a comma. These variables here, constant, slope 2, slope 1, have not been defined yet. Yeah, so I have to define them later on, so I'll do that on top of this. Yeah, but first look at what the observation is going to be. I also need to specify a sigma, and I'm going to say that's equal to sigma, and I'm going to specify sigma in a moment. And then very important, I specify what my observed variable is, and that's from my data frame the variable y. Yeah, so here I've explained to pymc3, to the model, that the observed variable, so ops, is normally distributed with a certain mean, mu, and a certain standard deviation, sigma. And we need to have this keyword here, observed, which then tells it which variable it's actually fitting. And it's fitting the variable dfy. So from the data frame, the variable y. So now there are a couple of things that we need to define. So one is constant. I need to say what constant is. And I need to explain what slope 1 and slope 2 are. Basically what happens here is that we're specifying the prior distribution of constant and of these other variables. So I'm going to say that constant is normally distributed. And again, we do the same as we did here. Here we had ops and we repeated the name of the variable. I'm doing the same here. So I have constant and I'm repeating the name of the variable constant. And I'm going to assume that it's normally distributed with mean 0 and standard deviation 3. Yeah, so this is artificial data, so it's very hard to understand how you should specify your prior for artificial data. So later on we're going to be working with real data, and then we can use our knowledge of our intuition of how that data has been generated to specify our priors on the parameters of our models. So another variable I need to specify is slope 1, so that's going to be normally distributed. Normal, repeat the name of the variable, and here I'm going to say it's normally distributed with mean 0 and standard deviation 2. Slope 2 is also going to be normally distributed, name slope 2. Mean is going to be 0, standard deviation is going to be 2. Yeah, so the fact that I specified that constant slope 1 and slope 2 are normally distributed means that they can be both positive and negative. And that seems sensible. But now finally I have to specify the standard deviation of my distribution, sigma. So that's the sigma that we've used here. And of course with sigma I know it's not going to be negative. Yeah, so I need to specify a distribution here that is restricted to only positive values. Yeah, so there are a number of choices here, and I'm going to choose half normal. So repeat the name of the variable, and I'm going to say it's half normal with parameter 1. So this now specifies my model. Then the only thing I need to do is to say that I want to trace sorry. So we're going to sample from this distribution. And basically everything is set now to run this model. Yeah, so now we're going to run it to see whether we didn't make any mistakes or any typos. You see the sampling process here, and it's already finished. So I didn't specify any parameters here for sample. So that means it takes the defaults, which basically means it's going to do 4 chains in 4 jobs. Yeah, so it's using 4 cores of my computer. And by now it has generated the trace. Yeah, we're going to look at the trace in the next video. So just briefly summarizing, we specified that with PM model, so these are sort of the keywords with which you start your model when you write down a Bayesian model in pymc3. You give the name of the model. Then for each of the parameters of your model, you specify a distribution. Yeah, this is going to be the prior distribution of that parameter. So here we have 4 parameters, the constant, slope 1 and slope 2, and of course sigma. Then we say the observable variable is normally distributed. Again, I repeat the name of that variable, ops. It's going to be distributed with certain mu. And here I specify my model. So here you see sort of the equivalent of an OLS model. Slope 1 times x1, slope 2 times x2, and a constant. I specify my sigma, and I say that the variable that needs to be fitted is, from my data frame, the variable y.